Hi class. So in this video we'll talk about power. And power is defined as the work done on an object divided by the time it takes. And work is an amount of energy. So energy is in joules and time is an amount of time. So it's in seconds. And there's a special, so power comes in useful for a lot of things in our day-to-day lives. So there's a special unit for power, which is joule over second. It is known as a watt. Not to be confused with work in this class. So watts is, so 1 watt is 1 joule per second. Okay. So to demonstrate how we are going to make calculations, I would like to do an example here. So let's say you have a 30-story building. So a 30-story building has a height of about 100 meters. And let's say you have some box or something down here of mass m. And let's say that the mass is 1,000 kilograms. And you have an engine on top of this. You have an engine here. Now that engine is hooked up to this mass through something like a pulley system. And what this engine is supposed to do, it is meant to be able to pull this 1,000 kilograms all the way up 100 meters. And someone asks you, okay, what is the power rating for our engine if we wanted to make the climb in, let's say, 1 hour, versus if we want to go a little bit faster and make the climb something like T2 is 10 minutes. Okay, so if you go ahead and the way you set this up then becomes, so you start with power equals to work over time. The first thing you need to figure out is work. So right now, forget about this time. So we have 2 times. We want to know the power for bringing this mass up in 1 hour versus 10 minutes. Forget about this for now, and let's work on finding work. Okay? So if you remember from our previous video, our full definition of work is if the energy initial plus whatever work you do on an object equals to its energy final. Now, let's say that the mass will be stopped here, right? So the velocity initial is 0. And when you get up here, it's also going to stop. So velocity final here is also 0. Okay. Good. So now, what we do is we expand this. So if you remember, the total energy is all forms of energy. In this case, we're just looking at kinetic potential, gravitational potential, because it's going up and down, and work done. So this is kinetic energy plus gravitational potential energy plus work equals to kinetic energy final plus gravitational potential energy final. Now we already said the kinetic energy will be 0 because it's not moving at the beginning. Remember, kinetic energy is the energy to do motion, so the thing is not moving. It doesn't have any. And then up here, we will allow it to get to rest. So kinetic energy here is also 0. Now the last thing is, remember gravitational potential energy. If you remember, let me just write this on the side here. Gravitational potential energy equals to mass times gravity times the point in the y direction you're at. So to save some time here, I'm going to set this as y equals to 0. And then up here, we'll set y equals to the height, which is 100. So gravitational potential initial is 0, because y is 0, 0 equals 0 times whatever this is, it's 0. So that's 0. And this here is what becomes our work. So that's the only thing left. So the work here is the gravitational potential energy final, which is mass times gravity times the height of the building. So we have work, right? So now work is what goes up here. All right, so let's go and work with this equation now. So power equals to work over time. This work is just the gravitational potential energy final divided by the time, which equals to mass times gravity times height divided by the time. Okay, now if you add all the numbers in here, so let's do the first case, which is in 1 hour. So first case is for t equals to 1 hour, the power is mass was 1,000 kilograms. Gravity is 10 meters per second squared. I'm just rounding it. Height is 100 meters. And here you have 1 hour. Now, if you want to turn this power into a watt, you better use seconds, because what you're going to get here is joules on the top, and joules per second will get you watts. So when you go ahead and turn 1 hour into seconds, it's 3,600 seconds. So at the end of this, you get somewhere in the ballpark of 277 watts. Okay, which is not a lot. So it does not take a lot of power, and 1,000 kilograms is the order of magnitude of a car. So this is, we're talking about lifting something nearly the size of a car, 30 stories up in an hour. So it does not take a lot of power to be able to do that. By comparison, for those of you who know what a horsepower is, so let's compare this. So 1 horsepower is 746 watts. Oops. Here. Forgot the unit there on the. Let's just do that. So this is 1 horsepower. Equals to 746 watts. And for those of you who are curious, a car, any car that is street legal is about, it's no more than 200 horsepower. As in a street car that has a 200 horsepower, that's quite a quick car. Most hover around the 150, I think, in the ballpark. Okay, so let's go back to the power calculation. So my question to you is, before we even do this, when we calculate for t equals to 10 minutes, what do you suppose the power is? Do you need a more powerful engine to be able to pull that faster, or will a less powerful engine do? So go ahead and try it out, see what you get. So if you carry out the calculation, power equals to work divided by delta T, and work is mass, gravity, height, divided by time, you know the only thing that's going to change here is this time, right? Which is 10 minutes. So when you go ahead and do this calculation here, you will find that it comes about 1,667 watts. Okay, so to go and pull this mass up 10 stories in 10 minutes, you require an engine that is a lot more powerful. and you can compare this. You know, this is this has to be a couple times more powerful. Okay. All right, so this concludes our energy segment. We'll have problems to do for homework on this energy section pretty soon. I'll talk to you all later. Have a good day.